Humans are explorers. From the beginning of time, we have always looked to what is over the next horizon. And space is really the last undiscovered frontier.
I think any animal explores. Our difference is that we're not just following the interesting smell. We're looking for the meaning of life. But our solar system is vast compared to us. So energy is key to the equation for exploration of our solar system.
Humans uniquely wish to explore, and we use energy to explore, whether it's wind power to move a boat across an ocean or rocket power to escape the surly bonds of Earth. Energy gives us the ability to go explore the universe.
1-0, and liftoff of Space Shuttle Atlantis.
We want to understand where we came from. What is this thing? Who are we? What are we? If there are other life forms, intelligent life forms, they're not in our solar system, I don't think. And so we've got to get out of this solar system. And that is not going to happen with the forms of energy that we have today.
The beautiful thing about space innovations is that we benefit here on Earth because we transfer that technology back here on Earth. Whether it's through our Wi-Fi networks, our satellite TV, through cell phones, water grids, power networks.
Pushing the limits of space exploration and technology is critical to improving the quality of life here on Earth. But also there's this natural unifying factor. It was just an American mission that went to the moon, but the whole world went with us.
The argument of, we have so many problems here, why worry? Humanity meets its end if we don't do it. It's that simple. We should find a way to thrive on Earth, live sustainably, but eventually the Earth dies. With absolute certainty, there's an end date. We should try to figure out how humanity can thrive outside of Earth. And we need to start immediately because right now we have no clue how to make that happen.
For millennia, the ability to travel beyond where our feet could take us was mostly the domain of the rich and powerful, who could command human labor and fleets of ships. Or kings and queens would have access to stables of horses necessary for longer expeditions. Energy gave us coal-fired trains, gasoline-powered cars, and jet-fueled airplanes, which gradually became accessible to us all. The miracles of energy have ensured that there is always a way to get almost anywhere in the world. And today, a small and growing number of people have even traveled into space. The miracles of modern energy launched humans into an era of exploration and discovery, reaching far beyond gravity's pull. Space may hold the keys to understanding ourselves, and we can understand space through energy. To understand ourselves and each other, we must understand the force behind the global events that shape the world. This is Power Trip, the story of energy.
To really understand the story of energy in space, we need to go to the beginning.
If you go back too far in history, people didn't really have a concept of what space was. They thought that the planets were just some sort of magical things that moved around the sky, so I don't think they really had a concept of going there. Once we, as a species, had come to the realization of what space really is, then I think the initial ways that people had in mind of doing this were guns. You would fire a projectile that would carry passengers, perhaps. There was a famous movie that was done around the turn of the 20th century that used just that technology to show people going to the moon. The thought of moving in the vacuum of space with a rocket was inconceivable to people up until fairly recently. Most people thought that a rocket required something to push against in order to move forward. That's not true at all. It's Newton's third law of motion that governs how rockets work. Physicists have known this for a long time.
That old Isaac Newton thought problem of if you have a cannon that can fire a cannonball fast enough, it will go into orbit. These fantasies about the idea of going into space date back to very early science fiction, and especially the science fiction that grew out of the Industrial Revolution of the 19th century. Konstantin Tsiolkovsky was one of those early imaginers of spaceflight and rocketry to whom we owe a great deal. Konstantin Tsiolkovsky was working a little earlier than the Wright brothers. He was a teacher before the Bolshevik Revolution in a very rural area of Ukraine. He was deaf, very nearly blind, but he continued to teach, and he was fascinated by this idea of sending rockets into space. He had spent a great deal of time writing up designs and drawings of what sort of technology would have to be made. He was one of the earliest people to come up with the concept of staging rockets, that you didn't have one engine that would shoot a payload up to its destination. You would have one engine that would accelerate the payload to a certain extent, that would fall away, and the next engine would take off. Here is a man who was doing this in isolation without any of the accoutrements of being a member of the elite, and he was drawing the fascination of many people, not only in Russia, but throughout the world. At this point, what Tsiolkovsky had done was purely theoretical, but along the time of the advent of the airplane and the development of aeronautics as an engineering specialty, these rocket enthusiasts got the idea, well, if airplanes can be created after all of these centuries of the idea, then the rockets can't be far behind. So you have these, by and large, men. There are a few women who were very interested in this idea of designing a vehicle that would accelerate fast enough that it would counter the Earth's gravity. Most of these rocket experimenters during the 20s and 30s spent a large amount of their time putting out brush fires. It takes a lot of skill to design a rocket that will achieve the altitude you desire and then go someplace else, and being able to do that remotely or pre-program it. Now, towards the end of free action in the USSR, as Stalin took over, these rocket groups were consolidated and became part of the Soviet state system. They weren't thinking so much about sending rockets into space. The Soviets were most concerned about defending the homeland against the German invasion.
Tsiolkovsky's visions of rockets to space had inspired people far beyond the borders of Russia. And by the time he died in 1935, German scientists picked up on the idea. But the dream of exploring the stars would have to wait. As war spread across the globe, rocket technology was developed as a weapon of destruction, and Nazi Germany pursued an ambitious rocket program.
Wernher von Braun was particularly important to the German rocketry program.
Von Braun was one of the absolute leading minds in that area in the world. He had visions of using rockets eventually to go to space, to go to the moon, to go to the planets.
The objective of Germany at that time was purely to win the war. The first year of the Eastern Front War was a disaster. They were seeking that super weapon that would solve their problem. Wernher von Braun had both the theory, the technical ability, and knowledge to work on these projects. They approached him, and he joined in. At age 25, he was put in charge of this rocket project.
Von Braun basically was able to demonstrate to the German command structure that this was a viable weapon of war.
Before that, you'd have to fly a plane over the city to drop a bomb. So it was much better from a military perspective to have a greater standoff distance when you launch your weapons.
They had already gone through this air battle over Britain, and the V-2 rocket was a trump card around that.
The V-2 was this great breakthrough because for the first time, the Nazis could send up a rocket and aim it in the general direction.
The V-2 was a true liquid rocket, and its propellants were alcohol, just ordinary ethanol, and liquid oxygen. They would distill the alcohol just as you would alcoholic beverages. Toward the closing days of World War II, the Germans were having very great difficulties with fuel supplies, and so using something that could be easily made from agricultural products was highly beneficial to the program.
The V-2 is terrifying because it felt like it could strike at any time from anywhere, and you wouldn't hear the buzz of a plane before the bomb comes in, so it seemed to come out of nowhere.
That's the frightening thing about rockets. It didn't sound like a wing of aircraft, so you didn't know when to hide.
The fear was it would give the military in Germany a decisive edge, and so there was a sense of urgency that the war had to be won soon before Germany became completely unstoppable.
The V-2 was used, but it was largely too little too late. When you consider these were concentration camp victims who were forced labor to work on them. And in fact, more people died in the production of those vengeance weapons. The real contribution of that V-2, it was the energy principle.
In 1945, as World War II is ending, the Soviets are coming in from the east, and the British and the Americans are coming in from the west. There wasn't just a race to win. There was a race to get to the equipment, to get the rockets themselves, but more importantly, to get the rocket scientists.
The space race had already begun. Both the Americans and the Russians saw the potential that the German V-2 rocket held. The ability to carry a liquid fuel which could be mixed incrementally without exploding all at once, to be programmed towards a destination with some semblance of accuracy, and above all, the collective experience of the German rocket scientists. Whichever side got the German technology and scientists first would hold a pivotal edge in refining the technology further and faster than the other.
The Soviet Union was coming into Germany out of vengeance. They were going to take revenge on Germany and their allies for what had been done in the USSR during World War II. There was no question in anyone's mind, especially in von Braun, that they would be treated better by the Americans than they would by the Soviets.
The rocket scientists often had to make a choice about what side they would go to. Generally speaking, the Russians got the bigger rockets, but the Americans got the scientists. In particular, the Americans got Wernher von Braun.
Once you had the hardware, you can always reverse engineer it. The advantage in the American side was having von Braun and his team. They could get a lot of questions quickly answered on the testing and the construction. Both the Americans and the Soviets worked with that V-2, and that is what was really the father of the first rockets that sent an object and then later humans into space.
Our country is at war, a war declared against us by the rulers of international communism.
The Soviet Union and the United States had been allies in the fight against Nazi Germany. But as the world began recovering from World War II, the United States had a decisive edge with atomic energy and weapons. With Europe divided between Soviet and American occupation zones, tensions began to simmer. The United States and its allies did not want to occupy the territory in Europe, but wanted to quickly put Germany back on their own feet to become a democracy. The Soviet Union wanted their communist ideology to dominate the European countries it had occupied. In 1945, writer George Orwell called this situation the Cold War.
It was a competing ideology between the free world and the communist world. Democratic forms of government and socialist forms of government, showing the world that a free market, democratic system of government could take on big challenges like this. That not only could we harness the resources and make great leaps, but we could do it in a way that inspired people and didn't oppress them.
And one of the most important and visible ways it showed up was with the space race, the race to get to the final frontier, with the idea that getting to space would reveal great technological superiority, but also a military competitive edge.
July 1st marks the beginning of one of the great scientific adventures of our time, the International Geophysical Year.
It just so happened that 1956 to 58 was declared the International Geophysical Year. Scientists and geophysicists wanted to send delegations, joint groups around to study solar activity throughout the world. That occurred just at the time the United States and the USSR were building these missiles that were both weapons, and they also had the option of being used as instruments of exploration.
The United States is proud to have a part in this great scientific undertaking.
Folks like von Braun in particular, while they were building military systems, their real passion all along was to put humans in space.
Both sides had declared that they were going to use their V2 products to explore, to send something to orbit the Earth, to contribute to the study of the International Geophysical Year.
The space race really is a story about harnessing energy. And it was a race between us and the Soviets to see who would figure out how to harness that energy first.
In the early days, the ability to lift a rocket in space was exclusively an energy problem. The amount of energy for lift is incredible.
Rocketry, the general principle is this: if I want this mass to go that direction, I need to throw some mass in the opposite direction. Newton's third law.
There's two different things. One is going into space and coming right back. And then the other thing is going into orbit. Once you get to orbit, you're actually kind of staying there for a bit. Basically, you're kind of falling around the planet, but you just never hit it. But to get to that speed requires a lot of energy.
And orbital velocity at low Earth altitudes is 17,500 miles per hour. So it takes a tremendous amount of kinetic energy to reach that orbital speed. And that's the key to a rocket. You have to burn something very fast to produce the hot gases that you then use to expel out through the tail and propel the rocket. You know, you look at that rocket standing there, and most of what you're seeing is fuel. Not only do you have to get the vehicle accelerated, but some of that fuel is going to go to orbit with you too. And so you're using up some of that energy to get the fuel accelerated. And so it's a very difficult set of problems to solve.
If you imagine a rocket taking off from a launch pad with this high-speed flame shooting out the nozzle in the back, it's pretty clear that's not firewood and it's not coal. Only from modern fuels could you get the energy density you need. Choosing what rocket fuel to use and how to manage it. It's all about getting more energy, more bang for the buck, so to speak, to lift the spacecraft higher and higher.
One of the very big leaps forward was done by Dr. Goddard in New Mexico. He started his experiments in Massachusetts, and his neighbors didn't like it very much because occasionally he'd have something go awry and he would burn up a cornfield or something. So he came to New Mexico over in the Roswell area, and he's widely credited with having invented liquid rocketry as we know it today. In fact, Wernher von Braun made a statement to the effect that I didn't have to invent anything. Goddard had already done that. All we had to do was apply sound engineering principles to improve it.
August 1957, the USSR launched the first ICBM. That was the first successful launch of a rocket that had the capability of going from one continent to another. But on October 4th, 1957, the USSR launched Sputnik, the first artificial satellite of the Earth, into orbit.
The energy to lift Sputnik into space came from the modern fuels in the lift vehicle. You get kerosene from petroleum. You get crude oil out of the ground, and as you refine petroleum, you get several things out of it. You get gasoline, diesel, wax, tar, paraffins, and kerosene. And kerosene was also the original motivation to get crude oil out of the ground as an illuminant, as something we would burn for light. We use kerosene to replace a lit candle, and in many ways the rocket's like a lit candle.
Suddenly, oh, wait a second, the USSR, that other side, have the capability of sending something into orbit. That means that they have a capability of sending nuclear warhead. And that was really a shock for much of the world.
Sputnik, a radio transmitter, would orbit the Earth and make a beeping noise that we could all hear. It was a way of telling the world we got here first.
Today, a new moon is in the sky.
It was scary, it was transformative. It was the October sky. And American satellites had been exploding on the pad. They weren't working well.
On the United States' side, the rocket engineers, and certainly President Eisenhower, Sputnik was not a great surprise. They knew they had launched the ICBM in August. He was very confident that Sputnik was really a blip, and they had a plan. They were going to launch a Vanguard rocket. Unfortunately, like many rocket launches, that was not successful. This time they decided we're going to go back to the Army ballistic missile development. And this is where von Braun's group had been working.
We finally launched Vanguard 1, and that was early March in 1958.
Explorer is in orbit, broadcasting to the world its coded scientific data. This close-up of the United States initiative.
But people knew the real test would be getting humans into space and returning them safely.
The USSR had sent the first living being into space, Laika, the dog. They'd never intended to bring her back. They had had a television camera take photos of the far side of the moon.
And then they followed up not that long afterward, putting the first human into space. And I would point out that that first launch of Yuri Gagarin, he actually orbited the Earth. We followed suit with Alan Shepard, but it wasn't an orbital launch. We just got him to a high altitude and said, hey, that was space. And so it looked like the Soviets were ahead of us.
From the position of propaganda impact, it was really embarrassing.
Can freedom in the next generation conquer, or are the communists going to be successful? That's the great issue.
John F. Kennedy had been elected on this platform that we were behind in the space program, that there was a missile gap. He went to his space commission, led by Lyndon Johnson, who had been a great proponent for space programs when he was in the Senate, and said, what can we do to beat the Soviets? The Johnson Commission said, look, we think we can get a man to the moon and bring him back by the end of the decade. They didn't tell him the price tag at the time, but given unlimited funding, they could do that.
To be sure, we are behind, but we do not intend to stay behind, and in this decade, we shall make up and move ahead. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked. Thank you.
That set a clear marker down in the space race, and it became about a destination. Who could plant a flag on the moon first?
When President Kennedy gave such a strict standard for success in such a short timeline, a lot of people thought it was crazy. Didn't seem possible. And the energy implications were significant and had not been solved.
You look at the airplane, most of the fuel is not even apparent. and actually uses the atmosphere to its advantage, they take the oxygen needed to burn that fuel out of the air.
But with a rocket, you have to take your oxygen with you because in space there is no oxygen. And so the designers build this very large object that had a lot of drag.
Designing space vehicles, there are numerous compromises that have to be made. Liquid oxygen, liquid hydrogen is a very good rocket fuel combination. Now, the problem with that is, however, that hydrogen also has a very low density. So it takes an enormous tank to contain that fuel.
If you're using liquid hydrogen and liquid oxygen, you have to cool it to like negative 400 degrees Fahrenheit or negative 300 degrees Fahrenheit for the oxygen. So that requires a lot of energy for the cooling to do the liquefaction.
Whenever you add humans into the factor, that adds to the energy because you not only have to carry the atmosphere, you have to carry water and food and bring them back again. So that is a tremendous amount of energy.
So many of these were energy problems. Carrying enough energy in the package that you have available to you.
Giant leaps had to be taken in order to harness the energy required to fulfill Kennedy's ambitious goal. From its beginnings under President Eisenhower and with great support from Lyndon Baines Johnson, NASA had made strides towards launching a person into orbit and returning safely with Project Mercury. Project Gemini spent 5 years developing ways to provide the energy needed to keep humans and spacecraft functioning in space for up to 14 days, as well as fuel requirements for maneuvering while in space. These steps paved the way for the Apollo program to set its sights on the moon. American astronauts traveled by jet to Iceland for training in manned lunar landings. Iceland's volcanic landscapes helped prepare the astronauts for what they might encounter. And during this time back in America, scientists worked on solving the energy problem. How would they build rockets carrying enormous amounts of fuel safely? But harnessing that much energy means dealing with enormous risk.
This is Mike Wallace at the CBS Newsroom in New York. America's first 3 Apollo astronauts were trapped and killed by a flash fire that swept their moonship early tonight during a launch pad test at Cape Kennedy in Florida.
January 27th, 1967, Apollo 1, just doing a test. The electrical system on board the Apollo module caught fire and it was wrapped in a nylon conductor, and nylon's very combustible. They had an oxygen-rich atmosphere inside the capsule for the astronauts to make it easier for them to breathe, so the fire spread quickly. And then they had a key design failure, which is the hatch opened inwards. But then what happens is when you have a fire on the inside, it makes the pressure higher. The pressure was too high to pull the hatch into the module. 3 people died, Ed White, Gus Grissom, and Roger Chaffee, and it was a national disaster.
The Apollo program had to be shut down in order to address these energy and mechanical issues. Meanwhile, NASA rocket scientists continued to address the massive undertaking of harnessing enough energy to launch a rocket beyond low Earth orbit, carrying a command module as well as a lunar landing module, all of which had to carry their own energy and fuel sources to create life-supporting environments and the ability to return to Earth. The Saturn V rocket was the vehicle designed by NASA to accomplish this task.
Going from that single engine of a V2 to 5 massive engines on the base of the Saturn V, getting them to work together and fire together, to figure out a way to keep the 2 fuels separated, only mix it when you want it to mix, not have it explode all at once. That takes a bit of skill.
One of the energy issues with any space vehicle is to be able to achieve the speed you need with the vehicle that you can actually build. We've solved it traditionally using staged vehicles. So the first stage burned kerosene and liquid oxygen. As it's burning off fuel, it gets lighter and it starts accelerating. At some point, it's used up almost all of its fuel in the first stage. It's jettisoned, and now the second stage takes over. Now, this is an advantage because you've thrown away all that dead weight, so you don't have as much mass anymore that you have to accelerate to orbital speed. At that time, it was thought that it would be very difficult to make a restartable kerosene engine because, if you've looked at an automotive engine, you use hydrocarbon fuels and you get deposits and thermal breakdown of the chemicals and all sorts of things. But a hydrogen engine burns very cleanly. So the upper stage used liquid hydrogen and liquid oxygen because it had to be restarted once it was in orbit to send the space vehicle on its way to the moon.
When you feel it, that's what it is. There we go. Thrust. Ignition. Confirm ignition and the thrust is go. Hey, Houston, Apollo 11 inside and gave us a magnificent ride. Roger, 11. We'll pass that on, and it certainly looks like you're well on your way now.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space.
We have these ages: Stone Age, the Iron Age, the Gasoline Age, and then the Space Age. This was a defining moment for an era that humans could go to the moon and come back. But it was also very important for the American identity that it was NASA, that a civilian program got there first. It was not a soldier conquering another planet, it was Americans going in peace. And we had tens of thousands of people around the nation contributing to the success of the space race. More people then were enslaved to build the pyramids. And it was sometimes NASA scientists working on thrust or combustion or rocket design, but also the suppliers, the people that built the rockets themselves. They were working on how to liquefy the fuel, how to store it safely, how to handle it.
That's a lot of the success of the space race is our scientists and engineers did a fabulous job in figuring that out. And if you look back at the technology that they developed, it's pretty amazing technology, even by today's standards.
It developed this whole new sector because we needed smaller electronics. A whole IT sector that gave birth to microelectronics, which led to smartphones, tablets, computers. The Apollo missions went to the moon 6 times, and the Apollo program was shut down, and we went to the shuttle program. Its intent was to be repeatable, that the spacecraft could take off and land dozens of times, and could carry more astronauts. So they needed a bigger astronaut pool, and it diversified and expanded the number of people who were space ready. It started to look more like America. These astronauts are not just physical heroes, they're all intellectuals too.
When I grew up, although I was enthralled by the concept of spaceflight, there were no astronauts who looked like me. I lived in the segregated South. My favorite way to spend my Saturday mornings growing up was to go to the local theater because that was the one day of the week we could go. And you sat up in the balcony and we watched 2 movies. One was usually Buck Rogers, and I loved the way he would walk out to his spacecraft lift off, go to Mars, and come back all in the same day. I was a NASA astronaut, still on active duty in the Marine Corps, and I had an opportunity to fly 4 times on the space shuttle. My second flight was aboard Discovery when we deployed the Hubble Space Telescope in 1990. It takes an extreme amount of energy to get into space. We're a 4 million pound vehicle. When you talk about the shuttle itself, then the 2 solid rocket boosters, and then the big external tank. Some people can speak in newtons, I don't. We talk about pounds of thrust, and so it's about 7 million pounds of thrust to get off the planet. There's a lot of energy that goes into a liftoff. The 3 main engines ignite first. It's attached by the 2 solid rocket boosters, 4 bolts each. And those 8 bolts kind of catch it as it falls forward. We call it the twang. And that takes a grand total of 7 seconds. In that time, the computers make sure it's okay to go, and then they send a signal to the 2 solid rocket boosters to ignite. When that happens, it gets exciting. The thing that's not what everybody thinks you're pressed back in your seat and it's like a lot of G, and it's not at all. It's like being in a car at a stop sign with a teenager who floors the accelerator. But you can hear and feel the explosion of the solid rocket boosters and just shakes the vehicle. The purpose for the solid rocket boosters is to get you up through the atmosphere as quickly as you can. And it's essentially a trajectory that's straight up through the atmosphere. And it continues to vibrate. After that 2 minutes, the solid rocket boosters are all spent and fall away. Then it gets really, really smooth. The acceleration begins to build up because the vehicle's now reduced to just the basic shuttle with the external tank, which is almost empty. You're now in a 200,000+ pound vehicle with 1.5 million pounds of force pushing you along. Think about the old F equals ma equation. There's a lot of force, not a lot of mass. Feels like you have a couple of gorillas sitting on your chest. As you get toward the 8.5 minute point, you're going 17,500 miles an hour. And then you're weightless. The bad thing is energy pushes you to 17,500 miles an hour, and then you got to get rid of it when you come back. That's the hard part on the vehicle. It's what makes re-entry very difficult. You know, energy is neither created nor destroyed, it's just being converted. That's a lot of energy to dissipate. It's 17,500 miles an hour worth of energy. And so you're converting the energy from kinetic and potential that you have on orbit to heat dominantly. The vehicle heats up to 3,400 degrees Fahrenheit on the bottom by just plummeting down through the atmosphere, letting the molecules of air bombard the vehicle. When we got to a place above Earth where we were happy to turn it into a glider, you want to have enough energy left for the vehicle to be able to get to the runway, which wasn't very far out. It was, 6,500 feet or so short of the runway. That energy gets eaten up again because of drag and everything else, and we lose it about 1 knot per second once you pull the vehicle up. People ask you, what happens if you don't like your approach? The answer to that is tough, because you only get 1 shot. It's a glider. As you get closer and closer to your desired touchdown point, the energy bleeds off to 0. You have no energy to go back around. Touch down, and hopefully it's on the runway.
The shuttle program launched 355 astronauts over 135 missions. During that time, the International Space Station was assembled and allowed for extensive research across a variety of fields. All of the leaps in energy technology gave us technology that we use today on Earth.
With more astronauts up there for longer, you can do more complex missions, but also do a lot of experiments. So the whole mission's changed from just beating the other guy to space to actually learning more about the human condition.
+20 years we've been on the International Space Station, we have made life dramatically more attractive, more survivable. Whether it's pharmaceutical products that we are able to do much more pure materials on orbit, or whether it's waste systems management, water purification, those kinds of things that you have to be able to do in a spacecraft. And we find ingenious ways to do it with very small equipment. We can bring that back to Earth. Were it not for the Apollo program, where we were going to put humans on another surface and we needed to know their vital signs. Can't run a cable 250,000 miles away, so wireless communications was developed to be able to communicate with spacecraft. Voyagers have left the solar system, and yet we're still communicating with them.
The ability to track goods and services around the entire planet with, centimeter level precision is one of the amazing things that you can only really do via space. I have an app on my phone that shows literally every single boat that's moving around the planet, on my phone. That used to cost probably millions of dollars to have, and now you can download it for $3.99 on the App Store.
On the International Space Station, it's like a medium-sized solar farm. They absorb the energy from the sun, convert it into electricity, put it into batteries. Going around Earth, you have 45 minutes of daylight, 45 minutes of darkness. When you're not in daylight, you're using the batteries.
Those technologies then get transferred down here to Earth, and you see them in the form of a battery that lasts much longer in your hand and your phone.
So from the very dawn of the space age, very early satellites, the people connecting the planet. And now what we see is, in a very data-driven way, that space is essential to solving global climate change.
The energy needs and requirements for space travel are very complex. And so there's a lot of energy learning we need just for the execution of the mission. But then the mission itself also reveals a lot about energy because it becomes the eye in the sky. And we can see more about the energy system's impacts on Earth from space sometimes than we can see from the ground. It not only teaches us how to use energy better, but shows us how we're doing it badly.
We track that mass of plastic debris that floats around the ocean. We're able to track the temperatures of the oceans thanks to satellite technology. We receive broadcasts from people from their cell phones when there are uprisings and oppressions going on. We're aware of what's happening to the Uyghurs in Xinjiang because of the space age.
When I was the NASA administrator, whether we flew 1 flight or 20 flights a year, it cost me about $2 billion to maintain the shuttle program. Whereas today, it's a lot less because what they're doing is they're purchasing a service. President Obama really believed that it was a better model, and he had a lot of people pushing from the outside.
So this is the next chapter that we can write together here at NASA. We will partner with industry. We will invest in cutting-edge research and technology. We will set far-reaching milestones.
Congress had written the law that said if there is a service or a capability that is available in the private sector, except in extreme cases, government agencies cannot compete with the private sector. There was no reason in the world NASA could justify not using commercial capability for transportation to and from space.
Part of it, the privatization of space feels like just a billionaire's ego show. Rich people going to space because they can. But there's this other element, which is we now have more devices, more information available than ever before. It has lowered the cost of telecommunications for us. We have access to information from around the world. So we all get benefit of this billionaire space race.
I love seeing billionaires spend their money on space because it's a signal that says this mode of transportation will become commonplace for the rest of humanity.
There was a time when air travel was only for the rich. Now anybody can travel for an incredibly low price when you think about it in terms of what you're getting for the dollar.
These old cars like the Stutz Bearcat, that wasn't available for the common person. And eventually we had mass-produced cars like the Model T Ford. Energy became cheaper for the fuels, and energy made the cars cheaper from the factories.
In the 80s, wealthy individuals had cell phones, but now even children under the age of 18 have cell phones. I'm not saying that everyone will have their own spacecraft or everyone will have their own rocket. We are getting to a place where a 16-year-old would be able to design an energy-efficient spacecraft that is reusable and may have been 3D printed.
It's always been the commercial sector that's made everything possible. If I had told somebody that we went to the moon on a commercial rocket, they'd say, "You're crazy." And I would say, no. NASA did not build any components for the Saturn V program that took us to the moon. We bought them. The federal government does a lot of the cutting-edge research, stuff that's risky or way too expensive for the private sector to do, and then they pass off the intellectual property so that the private sector can actually operationalize it.
I feel right now that we're living in like the next Renaissance. How did art and science really flourish during the original Renaissance? Small government grants and academics doing stuff? Not so much. Privatization is required in order to capitalize on science technology and migrate that from possibility to practice.
We're still in like chapter 1 of space's energy story. We're doing the basics. We're using chemicals to combust and push us via a controlled explosion off the surface of the planet.
Modern rocketry is based on fossil fuels. It's either the fossil fuel directly, like a kerosene mixture, or liquid hydrogen, which you typically make from methane or natural gas. And the amount of power is phenomenal. The space shuttle requires 12 gigawatts of power at liftoff. That's 100 times more than entire university campus, 100,000 people need on a hot day. And it consumes it over like 8 minutes. It's just incredible. But in the long run, if we want to go farther afield for longer, fossil fuels might not get us there.
Anybody who says, well, why do we need to worry about it? Fossil fuels have gotten us this far. That is true, but we want to go farther.
The energy we have today can almost certainly get astronauts to Mars. It's much less clear that the energy we have could actually get astronauts successfully back from Mars, and I'm not sure who's going to sign up for that ticket.
Right now, all the propellant you're going to need to go out to these distant places and come back, it has to all launch with you. That means you have to launch a massive amount of weight, which requires even more propellant. It's exponential. You have to carry more and more fuel just to carry more fuel. We need to develop how to make propellant in space and how to refuel spacecraft in space. That's what we need to find. For the foreseeable future, we are going to be using fossil fuels to get things into space. Longer term, though, I think as activities continue to expand and as technology improves in space, we are going to be using other sources of energy. Solar energy in order to separate oxygen and hydrogen from water molecules and make propellant that way, or making our own liquid methane in space. Nuclear thermal propulsion and other small-scale nuclear reactors that we can put in space, on the moon, or future bases on Mars, where we can generate a lot of our own power from clean nuclear sources.
One of the great things about this moment is that it's like the best time to get into space. Almost anything you can imagine under the sun is being pursued now. There's even a company which is basically trying to use a centrifuge to get something going super fast, and then at the right moment it goes, you know, straight up, and that's like essentially their first stage.
We're an alternative energy company. We've taken the rocket, which is seemingly impossible to make emissions free, and we've found a way to deliver that same capability using clean, renewable, sustainable electricity. We are, in most industries, moving away from chemical propulsion. It represents the electrification of the space transportation industry.
The G-forces that those payloads experience are in the thousands or even tens of thousands of Gs, so it is not a suitable way to launch humans because our bodies would never survive that. On the other hand, let's say we get serious about solar energy harvesting using an orbital platform. Then there's going to be a lot of stuff that has to be put into orbit, and this is an ideal platform for just doing this repetitively over and over and over again.
We are living at a time where we can combine innovation for the sake of exploration and fun, innovation for the sake of our planet. That's one reason I roll up my sleeves and work in space every day.
I'm trying to figure out ways to track 50,000 objects orbiting the Earth right now, ranging in size from cell phone all the way to the space station, where only 5,000 of these are working satellites and everything else is garbage. All things in space require energy. So to remove something, you have to remove energy. To get into higher orbits, you have to find a way to input energy. That's what keeps me up at night.
It is ultimately a matter of energy. I don't know if that's through nuclear or through some other phenomenon of physics that we don't yet understand. Just need more sources of energy in order to enable the kind of deep space exploration that a lot of us have dreamed about.
Energy is going to be the enabler, but it's also going to be the beneficiary. The technology that we have to develop to make these space missions practical is ultimately going to be used in people's homes and people's vehicles and all sorts of things, and so we will all benefit from it.
The photo that's been seen more than any other photograph in the history of the world is that of the entire Earth in full frame. There weren't actual boundaries between the countries. It revealed the environmental preciousness of our home. And the environmental movement was born at about the same time, and that's not an accident. A lot of people credit the space program for giving us a better insight into how valuable the Earth's ecosystem is.
I think if we're looking to become a multi-planet species so we can migrate from Earth to another place, once we've destroyed Earth, we're out of luck. Earth is the only planet in our solar system that likely can sustain human life for a prolonged period of time. I don't think people want to go to a place like Mars where you're going to live in a spacesuit the rest of your life. Nobody's going to come outdoors, take off their helmet, and take a big, deep breath of the great carbon dioxide atmosphere of Mars.
That's one of the unfortunate things about popular media right now is that they're portraying it as sort of like space or Earth. And I don't think anybody in the space community believes that. In fact, many of us are motivated by the idea that space is going to be necessary to understand Earth so that we can do our best to help have a sustainable future.
Space is critical for humanity to understand itself. In fact, I believe that space is the perfect mirror for humanity, for us to understand ourselves better.
And as we go deeper into space, we learn more, and it helps us to live better, healthier, and safer lives here on Earth.
5, 4, 3, 2,
We are centuries, if not millennia, away from taking everybody off of this planet. So we have to find a way to preserve this planet. There is a balance. We are going to have setbacks. We will have to figure these things out. We're the only life form on this planet that can plot out a goal of sustaining its own kind for generations, for centuries, for thousands of years.
I think for the foreseeable future, energy may well be the limiting factor on human expansion. So any breakthroughs that can be achieved in energy availability, energy supply, energy transport, and using that energy to go to space, to go to the stars eventually, is very important. I mean, humans have had this yen to explore forever, and I think we're just being true to ourselves when we do that.
Fantasies from the 19th century about rockets to the moon became reality because of the magic of energy and those who believed it was worth the effort. Space exploration brought us together to overcome extraordinary barriers. And the more we search for new forms of energy that will take us to the other star systems, the more we see how far we have to go. But it is in our nature to go further. And each of these small steps in energy innovation could become one giant leap for humanity.